Welcome to this next video in the playlist on field theory. In this video we are going to prove, as the title says, that if you have a finite subgroup, a finite multiplicative subgroup of a field, then that group is going to be isomorphic to a cyclic group. Okay, so I'll begin by writing that theorem out explicitly, and then what we'll do is actually prove a related theorem which will allow us to conclude that this theorem is true. Okay, so in symbols then, we can write this like so. Let's say that G is some subgroup of the multiplicative group of a field, the group of units of a field. Now, of course, in the case of a field, the group of units is all elements apart from the additive identity, so this will actually contain all of the elements of the field except 0. Okay, so G is a subgroup of the group of units of a field, and we're also going to assume that the order of G is some finite natural number, which I'll just call n. Okay, so we've got some finite subgroup of the multiplicative group of a field. Then the claim is that G is actually going to be isomorphic to the cyclic group on the set of n elements, or of order n, okay, which I'll denote Zn, which is of course a very simple group structure. Okay, so the structure of finite multiplicative subgroups of a field are very, very simple, is effectively the big theorem that we have to prove in this video. Okay, so we're going to prove this by proving a related theorem from group theory, and the first thing I want to do is state this related theorem and explain why proving this will allow us to conclude that this is true. Okay, so here comes this related theorem. Now, the related theorem does look complicated when you see it for the first time, because the conditions in the statement of this theorem, you might never have seen those before in group theory. Okay, so here goes. So the theorem is going to be that if we have a group, capital G, okay, which is a finite group, so let's say we've got some finite group, capital G, which has order little n, so I'll stick with little n to denote the order of the group in short, okay, and this group is going to have a special property, and it's this special property that you might never have seen before, and this is why this theorem might look scary initially when you see it. The special property that this group is going to have is that whatever, let's say, little d that you can find which divides n, okay, and what do I mean by this? Little d is some natural number as well that divides n, i.e. n is a multiple of little d. So to give an example, if we had n is equal to 10, okay, can you come up with all the possible little d's? Well, little d is equal to 1 would be an example, little d would be equal to 2 would be an example, little d equal to 5 would be an example, little d equal to 10 would be an example. So those would be all of the things which divide 10. Okay, so the special property that this group is going to have is you pick any d that divides n, then there exists at most d solutions in the group, so d solutions, which I'll call little x's, so d little x's in the group to the equation x to the power of d is equal to the identity element. Okay, that is the condition that we're going to want this group to obey, and then the conclusion is, then the theorem says that G is actually isomorphic to the cyclic group on the set of n elements. G is cyclic. Okay, so if this is true, if this condition holds, then you can conclude that your group is cyclic. So you've got some finite group of order, we're supposing little n here, and if in addition it satisfies this property that whatever little d you take that divides the order of the group, there exists at most d solutions to this equation, i.e. you raise the element to the power of d and you get the identity element. Okay, so you go through your group, capital G, you go through each element, all n elements, you raise them to the power of d, and you ask, do you get the identity element? You collect together all of the ones where you do get that as an answer. Those are the solutions to this equation, and I'm saying that for all the d's you get at most d solutions, so not more than d solutions. If your group satisfies that property, then you can conclude that it's a cyclic group. Now, why would proving this theorem then allow us to conclude that finite multiplicative subgroups of a field are cyclic? Well, let's have a look at why a finite multiplicative subgroup of a field is going to obey this property. Okay, so let's say we have a finite multiplicative subgroup of a field G here. Okay, if we're going to question for some d that divides the order of the group, is it the case that there is at most d solutions to the equation x to the d is equal to 1? Well, of course the answer is yes, because this equation, if we think about it in terms of field theory, this is x to the power of d. So take some element in the field, raise it to the power of d, multiply it by itself d times, and you're now going to get the identity element, which in this case is the multiplicative identity, 1. Okay, those are the solutions to this polynomial, x to the power of d plus the additive inverse of 1 is equal to 0. And what do we know is true in a field? We know that in a field, a polynomial has at most the degree of the polynomial distinct roots in that field. So in the entire field, capital F, there can be at most d elements that satisfy this. So certainly in a finite multiplicative subgroup of the field, there is going to be at most d elements that satisfy that equation. Okay, so indeed any finite multiplicative subgroup of a field is going to satisfy this property, i.e. it's going to be a finite group with this property true, and therefore if this theorem is true, we can conclude that it's cyclic. Okay, so this theorem is going to be our route to proving that a finite multiplicative subgroup of a field is a cyclic group. Okay, so everything now rests on being able to prove this theorem. So let's now actually begin the proof of this theorem. Okay, so the proof of this theorem is going to use the Seelof theorems in group theory. We're also going to use a little bit about p-groups, and also an understanding of internal and external direct products is going to be necessary. So if you go to the playlist on group theory, I have lots of videos on the Seelof theorems. I also have a video entitled p-groups, and a video entitled Internal and External Direct Products. Okay, those are going to be necessary in order to understand the proof of this theorem. Okay, so those are the prerequisites laid out, and of course basic group theory is obviously a prerequisite as well, but I won't explicitly state that. Okay, right, so we'll start then with a finite group which we're going to suppose obeys this condition, and we want to be able to prove that it's isomorphic to the cyclic group on the set of n elements. Okay, so the first thing I'm going to do is I'm going to take the order of my group here. Okay, and I'm going to split it down into its prime factorization. So n here might split into the prime factorization p1 to the power of alpha 1 times p2 to the power of alpha 2, all the way down to, let's say, some prime ps, where s is of course a natural number, to the power of alpha s. So this is just a general prime factorization. Okay, so I've just split this natural number into its prime factorization in the way that you learnt to do in primary school. Okay, right. Now, the first Seelof theorem tells me about the existence of Seelof P subgroups. It tells me about the existence of a subgroup of order P1 to the power of alpha 1, of order P2 to the power of alpha 2, and all the way up to PS to the power of alpha s. Okay, so by the first Seelof theorem, at least one subgroup of each of these orders must exist inside the group. I claim that because this is true, only one Seelof subgroup of each size is going to exist. Okay, so there is going to be one Seelof P subgroup, Seelof P1 subgroup here of order P1 to the power of alpha 1, and I will call that capital P1. There is going to be only one Seelof P2 subgroup here of order P2 to the power of alpha 2, which I'll call P2, etc., all the way down to there will be only one Seelof PS subgroup of order PS to the power of alpha s, which I'll call capital PS here. Okay, and therefore all of these Seelof P subgroups, or Seelof subgroups rather, I shouldn't say Seelof P subgroups, all of these Seelof subgroups will be normal. So all of these will be normal subgroups of our group capital G, because if they're the only subgroup of that size, then when you conjugate them by any element of the group, it must take you back onto another subgroup of the same size, but they're the only subgroup of that size, so they must be stable under conjugation by any element of the group. Okay, right, so how can I prove that there can only be one Ceilov subgroup for each of these primes, P1, P2, all the way up to PS? Okay, well the reason is that this is true. Okay, if I have a Ceilov, let's say P1 subgroup, so let's just do the argument for the prime P1. Okay, so P1 here, capital P1, is an element of the set of all Ceilov little p1 subgroups of G. I claim that it's the only element in that set, and the reason it can be the only element in that set is if you think about all the elements in this subgroup, how many elements are there in that subgroup? There's going to be p1 to the power of alpha 1 elements in that subgroup. Okay? All elements in a group must have order that divides the order of the group. Okay, i.e. when you raise them to a certain... Well, remember what the order of an element is. The order of an element is the smallest power that you have to raise that element to get the identity back again. Every element of the group must have an order that divides the order of the group, because remember, you can generate from any element its cyclic subgroup, which must have order that divides the order of the group. Okay? So, what that means is every element is going to have an order which, if I raise that to a higher power, is going to become p1 to the power of alpha 1. What I'm trying to say here is that if you take any element of this subgroup and raise it to the power of p1 to the power of alpha 1, okay, this number here, you raise it to that power, you will always get the identity back again. Okay, this is a general thing that goes for any group. You take whatever finite group you like and take any element in that group and raise that element to power the order of the group, you must get the identity back again, because any element must have order that divides this. Okay, so effectively what you're doing is just taking an element, raising it to the power of its order, and then raising it to a higher power still, because its order divides this. Okay, so you're just taking 1 to a certain power. So think for yourself why this is the case, but I guarantee you that this is the case. If you take any element of a group and raise it to the power which is the order of that group, you will get the identity back again. So every element of this Ceilov little p1 subgroup of G is going to satisfy the equation x to the power of p1 to the power of alpha 1 is equal to 1. Now, of course, p1 to the power of alpha 1 is such a D, okay? It's something which divides the order of the group, okay? It's part of the prime factorization here. So, what does this then tell us? There must be at most p1 to the power of alpha 1 solutions to this equation. I've just found p1 to the power of alpha 1 solutions to this equation. So what that tells me is that there cannot exist another Ceilov p1 subgroup, because if there was another Ceilov p1 subgroup, that would contain another p1 to the power of alpha 1 solutions to this equation, which would contradict this being true. Okay, so this is the reason that I can conclude that there is only one Ceilov subgroup for each of these primes. There is one Ceilov p1 subgroup, there is one Ceilov p2 subgroup, all the way up to ps, there is one Ceilov ps subgroup, and this is the notation I'm going to use for those unique Ceilov subgroups relating to each prime. Okay, so if your group has this true, it's going to be true that there is only one Ceilov subgroup for each of the primes. Okay, and you might think, well, where on earth is this heading? Well, what I'm about to claim is that the group is going to be the direct product of these, but let me just make one more comment firstly. Okay, the intersection of these Ceilov p subgroups. Okay, so if I take one and intersect it with another, so pi intersect pj is going to equal the trivial subgroup if I is not equal to j. Okay, so if you take any two of these Ceilov subgroups here and intersect them the two of them together, you must get the trivial subgroup. And why is that going to be? Okay, well, think about the orders of these. The Ceilov pi subgroup, this has order pi to the power of alpha I. The Ceilov pj subgroup, this has order pj to the power of alpha j. Okay? The intersection of these two is going to be a subgroup of both of them, and therefore must have an order that divides both of them. What is the only possibility for a number, a natural number that divides both pi to the power of alpha I and pj to the power of alpha j, well, of course, that's 1. Okay, and that's the argument as to why the subgroup that you get when you intersect those two together must be the trivial subgroup. Okay, so if I intersect any two of these normal Celof subgroups in my group capital G, I'm going to get the trivial subgroup. And now what I claim is that my group capital G that satisfies this condition here is going to be isomorphic to the direct product of these Celof subgroups here. So the direct product of P1 with P2 with all the way along to PS here. Okay, and we will prove this in the next video, but before we just take a break, let me explain where this is going. What we are going to do is we are going to prove that later on, after we've proven that this statement is indeed true, we're going to prove that each of these Celof subgroups is actually a cyclic group. Okay, so each of the Celof subgroups is a cyclic group. And then what we are going to prove is that because all of them are cyclic groups, and because all of their orders are relatively prime to one another, that then implies that the entire group is a cyclic group. So that's where this is going. That's where this exploration of the structure of this group, which has this new condition true on it, is actually heading. Okay, so if you can't fully appreciate the direction that the argument is taking yet, I hope that that has helped a little bit. Okay, so we'll take a break here, and in the next video what we'll do is start by proving that G is actually isomorphic to the direct product of its Celof subgroups here that are all normal inside G, and then what we'll do is prove that these Celof subgroups are all cyclic, and then use that to understand why G is going to be cyclic.